It is spring. Okay, so good evening to all of you. So today we will start our portion on the magnetic materials, and what we are going to cover in today's lecture is magnetic moments of electron and free atom. Then we'll talk about dia, para, ferro, ferri as well as antiferromagnetism. We'll talk about the theories of paramagnetism and ordered magnetism. Then we'll cover magnetic phenomena like hysteresis and related properties. We'll talk about magnetic anisotropy, magnetostriction, magnetoresistance, and magnetic domains, domain theory, magnetization processes in terms of domain theory. We'll also look into application of magnetic materials, giant magnetoresistance materials and their applications, ferroelectric RAM we'll talk about a little bit, then electric effect followed by multiferroic materials and their applications. So we'll gradually build up the entire thing. So we'll first start with a little bit of history of magnetism, and then we will talk a little bit about the different kinds of magnetism, whatever is there. We'll refresh your memory, and then we will gradually we'll build up on the different concepts. So the first known magnets were naturally occurring lodestones. This is a type of iron ore like magnetite Fe3O4. So people of ancient Greece and China, they discovered that a lodestone would always align itself in a longitudinal direction if it was allowed to rotate freely. And this property of lodestones allowed for the creation of compasses 2000 years ago, which was the first use of magnet. So the first use of magnet was about compass. Then in 1263, Maricourt, he mapped the magnetic field of a lodestone with a compass, and he discovered that a magnet had two magnetic poles, north and south poles. Then in 1600s, William Gilbert, he concluded that Earth itself is a giant magnet. Then in 1820, this Danish physicist Hans Christian Ørsted, who has this famous Ørsted equations and theories, he discovered an electric current flowing through a wire. It causes a compass needle to deflect, and he showed that magnetism and electricity were related. Then in 1830, Michael Faraday and Joseph Henry independently discovered that a changing magnetic field produced a current in a coil of wire. And in 19th century, Maxwell, a Scottish physicist, he mathematically unified the electric and magnetic forces, and he also proposed that light was electromagnetic radiation. Then in late 19th century, Pierre Curie, he discovered that magnets lose their magnetism above a certain temperature that later came to be known as the Curie point. And then in 1900s, again, scientists discovered superconductivity. So superconductors are materials that have a zero resistance to a current flowing through them when they are at a very low temperature. And they also exclude magnetic field lines, which is the Meissner effect, which makes the magnetic levitation possible. So now all these bullet trains and all which runs on this magnetic levitation, this entire theory was discovered in the 1900s. So now refreshing a little bit about the electric and magnetic dipoles. This electric fields, due to the electric dipole, affect any charge in the vicinity, but the magnetic field, it only affects moving charges. So as with charges, what happens is opposite poles attract, like poles repel, and so this force which is exerted on a charged particle by a magnetic field is given by this vector cross product of QV into B, where F is the force vector, Q is the charge of the particle, V is the velocity of the particle relative to field, and B is the magnetic field. So if you look into the units, what you find is 1 Tesla is nothing but 1 Newton divided by your coulombs into meters per second. And so that is basically 1 Newton per ampere meter. So 1 magnetic field or 1 Tesla, this is a very powerful magnetic field. And so normally what previously people used to use is the Gauss, and this is nothing but 1/10,000th of a Tesla. Earth's magnetic field at the surface varies, but has the strength of about 1 Gauss. Okay, so these are the magnetic field units. So what is the origin of magnetism? There can be two origins. One can be macroscopic, which depends on the charge currents, and the other is microscopic, which is in the atomic scale. So what you have is, if a loop of area A is carrying a current I, then the intrinsic intensity of the magnetic field is given by the magnetic moment vector m or mu directed from the north pole to the south pole. So the magnitude of m is given by m is equal to Ia. Okay. Then the magnetic moment is the measure of the strength of the magnet and is the ability to produce as well as to be affected by a magnetic field. So there are a few important quantities in magnetism which you should now revise before we actually go into in depth of magnetic materials. So one is the magnetic moment vector, which I said is already Ia, or this is the measure of the strength of the magnet. Then you have magnetic field strength or magnetizing force H, and this is the measure of the strength of the externally applied field. Then you have something which is known as magnetic moment per unit volume or magnetization. And this magnetization, it measures the material's response to the applied field H. Then you have something which is known as magnetic induction or magnetic flux density, B, which is magnetic flux per unit area. And this is the magnetic, B is the magnetic flux density inside the material. So B is nothing but mu zero, where mu zero is the magnetic permeability of vacuum, and this is multiplied by your H plus M. So this together is going to give you a magnetic induction or magnetic flux density B. Then you have some units which is known as permeability. This is dimensionless. Mu is nothing. Permeability mu is B by H. Magnetic susceptibility chi, which is the volume susceptibility. Again, it is dimensionless, and this chi is equal to magnetization by this H. And then you have something which is known as mass susceptibility, molar susceptibility, and along with the names given to it, you have these quantities like mass associated with it or moles associated with it. Then you have energy of a magnetic moment E, which is given by the scalar dot product of M into B. And you have something which is known as magnetic anisotropy, which means that various directions in the crystals, they are non-equivalent with respect to magnetization. And this implies that M may not be in the same direction of the applied field. There are many contributions to this anisotropy, as we shall see later. Crystalline magnetocrystalline anisotropy is the most prominent of this magnetic anisotropy, and we'll find a lot of applications of this magnetic anisotropy in the coming slides. So what is response of a magnetic material to a magnetic field? So that is magnetic susceptibility, as I said, chi, that is delta M, which is magnetization by the applied magnetic field, which is delta H. So classification based on response to a magnetic field, you have two different classifications. One is paramagnetic, so you're attracted by a magnetic field, or it can be diamagnetic when it is repelled by a magnetic field. So what are the sources of magnetism? So charges in motion, as in current, they produce magnetic field. So this is one source of magnetism. Another source is the electron itself. So electrons behave as if they were tiny magnets. So every electron in an atom behaves as a magnet in two ways, and each having two magnetic dipole moments. So you can have a spin magnetic dipole moment, or you can have an orbital magnetic dipole moment. So one, you can say very crudely, is due to the rotation of an electron, whereas the other is the revolution of electron, but that is not exactly the case. But the one is because of the spin of the electrons, the other is because of the orbital motion of this particular electrons. So spin and the orbital magnetic dipole moment, if you see, it looks somewhat like this. So as I said, the origin of magnetism, the atomic origin of magnetism, it can happen is due to, one is due to the spin of the nucleus, and this is a very small effect. It's not really very much not to be considered in a substantial manner when you are having something at the room temperature. Of course, when you go to very low temperatures, then this particular spin of the nucleus becomes very important. Then you have something which is due to the electrons. Out of this, there are two, as I said. One is due to spin of the electrons, the other is due to orbital motion of the electrons. So the magnetic moment due to spin is equal to the magnetic moment due to orbital motion, and this is approximately expressed in terms of the Bohr magneton units. So this Bohr magneton, or mu b, is Eh by 4 pi m, and the value is given over here in the slide, as you can see. So if you have to understand magnetism, you have to understand the effects which is observed. So one is direct coupling, which is moments, that is spin, orbital motion, or your nuclear. They are localized to an atom, and their direct interaction with moments in neighboring atoms. So that is direct coupling. Another is mediated interaction, moments or magnetism arising from itinerant electrons in the bands of metals with the possibility of mediation of interaction via free electrons. So that is also another kind of interaction, which is mediated interaction. And the next is the super exchange. So you have local magnetic moments which interact with other local moments via mediation of non-magnetic elements. That is a super exchange. So example, you have antiferromagnetism in MnO. So these are known as super exchange mechanisms. So from magnetism of the fundamental components to the magnetism of devices, if you look into it, this fundamental components you see over here, you have electron orbit, you have electron spin or mu nuclear spin. This gives rise to the magnetism of atoms. Then what you have is magnetism of the solids. And you have this magnetism of the molecules coming in. So you have these different kinds of interaction. One is the spin, the other is orbital motion, and the lattice. So spin and lattice interaction is the weak one. Spin and orbital motion is also weak, whereas lattice with the orbital motion is a very strong interaction. So these are the different things you should understand, how basically these different effects are there and what role it plays. So there are other parameters also to comprehend magnetism in solids, which is effect of the external magnetic field. So diamagnetism and polyparamagnetism are effects of external magnetic fields and do not arise independently from fundamental atomic entities. And there is another effect, which is effect of temperature, like ferromagnets become paramagnets at the Curie temperature. Alignments of magnetic moments in a paramagnet due to a field is thermally assisted. So these kind of concepts you have to kind of remember before we move in deeper. So you have, if you have the types of magnetism, so all matter, they show something which is known as diamagnetism. Then you have something which is arising out of the band structure of metals, among which you will find polyspin paramagnetism, you will find band ferromagnetism, and you will find band antiferromagnetism. We will not cover this portion in details. This we will just touch upon. But what we are more interested in is this, which is arising out of the atomic magnetic moments, which is permanent, spin, and orbital. So in one you have non-interacting atomic moments, which is the Curie paramagnetism, whereas the other you have is the interacting atomic moments. So you have ferromagnetism, you have ferrimagnetism, and you have antiferromagnetism. So this is what we will be totally discussing about. We'll talk a little bit about ferromagnetism, ferrimagnetism, as well as antiferromagnetism. So first, a little bit about diamagnetism. So you have paired electrons. In this case, this chi is negative. It is temperature independent. And the examples are hydrogen, water, sodium chloride, benzene. So it's something like this. So if you place this, you have this magnetic field H, which is there. It has been applied. And you place this particular matter inside the magnetic field. What you see is that the magnetic lines of force gets deflected out. So that means that this particular material is diamagnetic. Okay. So if you have this chi value versus this T, this is how the diamagnetic materials is going to look like. Whereas if you have a paramagnetic material, then it has unpaired electrons. Diamagnetic always has paired electrons. Paramagnetic has unpaired electrons. In this case, the chi value, the permeability value is positive. It decreases with temperature. And what you find, what are the examples? You have oxygen, you have copper sulfate, you have diphenyl picryl hydrazide. So these are all paramagnetic materials. So you see, if you put this material in the magnetic field, you find this that the magnetic lines of force are getting closer. So it is attracting the magnetic fields of lines of force through itself. So that is why this is known as a paramagnetic material. And this is how this chi value changes with temperature. You see that as you increase the temperature, it kind of exponentially it goes down. Okay, so this is the Curie law where chi is equal to C by T. So a simplified understanding of diamagnetism, which is based on the Lenz's law, is shown in these two particular figures. So in case of A, what you find is the electrons paired in the same orbital moving with a velocity v, and they are kind of cancelling each other. It's magnetic moments. Whereas in B, what you see is the effect of an increasing magnetic field, which is this B, which you applied over here on the magnetic moments. So what you see over here is that M1 is increasing, M2 is decreasing, so that the net magnetic moment, it opposes the field B. Okay, so that is why in case of paramagnet, what you see is that as you applied the magnetic field over here, for a paramagnetic material, this magnetization, it increases, as you can see over here, whereas in case of diamagnetic material, you see a slight decrease. So this is the MH plot for a diamagnetic substance, and as well as that for a paramagnetic substance. So there are two different kinds of paramagnetism. So that arising when the atom or molecule has a net magnetic moment, and that which is arising out of band structure, which is polyspin or weak spin paramagnetism. So if the net magnetic moments within the atom or molecule, they do not cancel out, then the material is paramagnetic. So oxygen, like, it has a net magnetic moment of 2.5 Bohr magnetons per molecule. Okay, so you have to understand that though there are many electrons in the atom, most of the moments cancel out. So what is left behind is only a few Bohr magnetons. In the absence of external field, these magnetic moments, they will point in the random direction, and the magnetization of this entire specimen is zero. But when a magnetic field is applied, two factors come into the picture. You align the force of the magnetic field and the disordering tendency of temperature. So there are these two different things which are occurring at once. So when you are applying an external magnetic field, all this random magnetization, whatever magnetic moments you see, they tend to align across the magnetic field. And the other is, if the temperature is increasing, then you see a disordering tendency of the temperature. So the combined effect of these two factors is that only partial alignment of the magnetic moments is possible, and the susceptibility of paramagnetic materials has a small value. For example, oxygen, it has this chi-m value 20 degrees centigrade. It is around 1.36 into 10 to the power minus 6 meter cube per kg. Now these two types of paramagnets, it can be differentiated. So those which are always paramagnetic with no other details to be considered, or which are ferromagnetic, ferrimagnetic or antiferromagnetic, and they become paramagnetic on heating. So these will have non-zero values for theta in the Curie-Weiss law. So effect of the temperature, if you see, any magnetic alignment, which is an ordering phenomena, is always fighting against the disordering effect of temperature. So you have this chi-m is equal to C by T minus theta. This is known as the Curie-Weiss law. So this chi-m is the mass susceptibility, which is given in meters cube per kg. C is the Curie constant, and theta is the unit of temperature and is a measure of the interaction of the atomic magnetic moments. Okay. So if you look into it, if there is no interaction between the atomic magnetic moments, then theta is 0, and then the Curie-Weiss law, this reduces to Curie law. But if you have something like an interaction happening, in that case, it becomes the Curie-Weiss law, and you have this theta, it is positive, usually with a very small value, or it can be negative. So negative values of this theta imply that the molecular or the atomic field is opposing the externally imposed field, and thus decreasing the susceptibility of the material. So now if you plot this chi-m versus T over here, you see how for the Curie law it looks like. So this is for the Curie law, this particular plot you see. This is for the Curie law. Whereas for the Curie-Weiss law, you have at this T value, there is this theta value coming in, and this is how the Curie-Weiss law, when you are plotting chi-m versus T, this is how it is going to look. So now we talked about the cooperative magnetic interactions. So ferromagnetism, if you see, you find in iron, you find in cobalt, you find in chromium dioxide. Antiferromagnetism, in this case, you find that the magnetic moments, they are kind of, one is going up, the other is going down. So the direction of the magnetic moment differs in case of antiferromagnetism. Whereas in case of ferrimagnetism, you do have these magnetic moments, in opposite directions, but the actual value, the quantitative value of the magnetism, it kind of differs. So if you look into Curie-Weiss law, this chi is equal to C by T plus minus theta, as I said, depending on what kind of interaction you are having. So if you look into a paramagnetic material, if you are plotting 1 by chi versus T, this is how the plot is going to look. For ferromagnetism, it is going to look somewhat like this, as you can see over here. And the Curie temperature Tc is given by this intercept of this particular line on the temperature axis. And in case of antiferromagnetism, this T value, you can see this intercept, it kinds of is in the negative region. So this is how we have all these different temperatures. So you have a Curie temperature in case of a ferromagnetic material. You have something which is known as Néel temperature in case of an antiferromagnetic material. Whereas in case of ferrimagnetism, you see the plot looks very much equal to the ferromagnetism, but you see a small curve over here, this particular curve, and this indicates it is a ferrimagnetic material. So basically it is having magnetic moments which are opposing to each other, but they are quantitatively different. Now, magnetic permeability versus coercive field. So if we apply a sufficient magnetic field to produce complete saturation inside the ferromagnet and then start reducing the field back to zero, we will find that at zero applied field, some residual magnetism is still left over here. As you can see over here, some residual magnetism is still left, and this is known as the remnant induction. And what you will require is a significant field known as coercive field to completely demagnetize this material. So over here you have this area which is known as the coercive field. This you apply. So if you are plotting, the coercive field versus the relative permeability, you find for different materials, if you plot it, you will see that materials which have a very large magnetic permeability, basically which means that it has a very large saturation magnetization, they exhibit a very small coercive field and vice versa. So this is how it works. So now we come to the important point of magnetic anisotropy that we had actually discussed, when we were talking about, the different terms. So what is magnetic anisotropy? Reiterating what we had already discussed, it is a dependence of magnetic properties on the direction of the applied field with respect to the crystal lattice. So what happens that depending on the orientation of the field with respect to the crystal lattice, one would need to lower or higher magnetic fields to reach the saturation magnetization. So you have something which is known as easy axis, and you also have something which is known as hard axis in the crystals. So easy axis is a direction inside a crystal along which a small magnetic applied field is sufficient to reach the saturation magnetization. Whereas hard axis is the direction inside a crystal along which a large applied magnetic field is needed to reach the saturation magnetization. So now if you have a body-centered cubic iron, the highest density of atoms is in the 111 direction. And so consequently, this 111 is the hard axis. So you see the magnetic field needed for it to achieve the highest possible saturation magnetization is here. Whereas if you look into the easy axis, which is the 100 direction where the atomic density is the lowest, in that case, it is only at this particular magnetic field you find that the saturation magnetization is reached. So that is why this is known as magnetic anisotropy. So along different directions, you have to apply different amount of external magnetic field to obtain the saturation magnetization. And so this depends with the different crystal structures. So for an FCC nickel, you will find that 111 is the lowest pack direction and that becomes the easy axis, whereas 100 is the hard axis. Whereas for a hexagonal cubic pack lattice of cobalt, you will find that the 0001 is the lowest pack direction, and so that becomes the easy axis. So this is how basically with magnetic anisotropy, you find a different amount of external field is required for you to get the saturation magnetization. And so you have this magnetic anisotropy. If you have, this is the equation how you will write it. So this EA, this is equal to your UN sine to the power n theta, and you have to sum it over n equal to 1 to infinity. And what is this theta? Theta is the angle between the magnetization and the easy axis, and K mu m is nothing but the UN is nothing but the anisotropic constant. So this is the anisotropic constant, and this is how you can actually write what is the energy associated with the magnetic anisotropy. So magnetic anisotropic energy, this is particular equation which you have to remember. So for a cubic material with 3 easy axes, the anisotropy energy is written by this particular equation over here. This alpha I over here, this is cos theta I, and theta I, these are the angles between the magnetization and the easy axis. So if you plot anisotropy energy versus the magnetization angle, this is how your anisotropy energy is going to vary, okay, with the magnetization angle, that is the angle theta. So the physical origin of the magnetic anisotropy energy is the interaction of the mean exchange field and the orbital angular momentum of the atoms or ions in the lattice. And this interaction is referred to as the spin-orbit coupling. Okay, so this is how it is going to look. So now we will derive the hysteresis loop for a single domain ferromagnet. So we'll start with an anisotropic ferromagnet sufficiently small, so it consists of a single magnetic domain. So you have a single magnetic domain, that is all the magnetic dipoles are aligned in the same direction, maximizing the total magnetization M. Assuming that the angle between the magnetization and the easy axis is theta, so this is how it is looking. So this is your easy axis, as you can see over here. This is the angle theta which is given, and this is your magnetization direction. So the magnetic anisotropy energy, which is EA, this will be almost equivalent to Ku sine squared theta. So now when an external field is applied to the ferromagnet, in addition to the anisotropy energy, we will also have a magnetostatic or Zeeman energy. And this magnetostatic energy is nothing but H ms cos theta minus phi minus theta. This phi is basically the angle with the easy axis which this external applied magnetic field is making along with the easy axis. And then you have something with the magnetization, which is that theta. So H is the applied magnetic field, Ms is the saturation magnetization, and phi is the angle between the applied field and the easy axis. So now what is going to be the total energy? So total energy is nothing but your anisotropic energy plus this magnetostatic energy. So you have this total energy as Ku sine square theta plus HMS cos phi minus theta. So now you have to consider two important special cases for the direction of the magnetic field. You can have either along the easy axis or along the hard axis. So if you have a hard axis magnetization, then this phi is equal to pi by 2. So in this particular case, the derivation of the total energy is nothing but Ku sine square theta plus HMS sine theta. So now we will find an angle that minimizes the energy in this particular case. And if you actually do the derivation, this is done in this slide, but later on you can actually work out with a pen on paper, you will find that the only way the conditions which are shown over here satisfied is if this particular external energy is 2 ku by ms, or ku is equal to HAMS by 2. So this HA is nothing but the anisotropy field, or field at which the magnetization reaches saturation. So for fields below the anisotropy field, from the equation dE by d theta equal to 0, you will also find that this sine theta is equal to minus m by ms. And if you put into this particular equation, you will find this m value is nothing but saturation magnetization into H by HA. So we find that for hard axis magnetization changes, linearly with the applied field until it reaches the saturation. So this is basically the derivation which is the angle that minimizes the energy. Okay, and for easy axis magnetization, in that case, the phi is equal to 0. Okay, because over here, as you can see over here, for the easy axis magnetization. So in this case, the total energy is Ku sine square theta plus H ms cos theta, which in previous case was your sine theta. So now in this case, energy will be minimized for all magnetic fields with the values between this minus 2 Ku by ms and 2 Ku by ms plus 2 Ku by 2 ms. So the coercive field in this case is 2 Ku by ms. So all of these fields will yield saturation magnetization. This results in the ideal rectangular shape of the hysteresis loop. So now if you look into it, for an ideal hysteresis loop, this is how it is going to look. You should actually get a perfect square. So when it is along the easy axis, this m value is directly along the x-axis, whereas if it is along the hard axis, then it should be along your y-axis. But this actually doesn't happen, and what you see is basically that kind of a oblong kind of a shape. So we will never find this kind of shape until and unless you have something, a permanent magnet like high Hc and Mr, which is hard magnets with a very high Tc. And in case of transformers, what you will find is these are soft magnets. So wherever this Hc value is more, then you call it as a hard magnet. When this value is very less, then you call it as a soft magnet. Okay, so Hc value actually determines whether it's a permanent magnet or whether it is a soft magnet. It's a hard magnet or a soft magnet. For information storage, mostly we look into soft magnets, which has very unique hysteresis loops. Okay, so now the alignment of domains, if we see, leading to magnetization of the sample. So preferential alignment of domains can be brought about by an external magnetic field. So during magnetization, the domains orients favorably, that is along the field direction, and grows at the expense of the unfavorably oriented domains. So if you have different magnetic domains inside a particular magnetic material, what happens is when you are applying the magnetic field, so during magnetization, these domains, they will all start to orient favorably along the field direction, and they will grow at the expense of the unfavorably oriented domains. So it can take place by two different motions. One is the domain wall itself is moving. So there's a domain wall motion, and the other is by rotation of the magnetization of the domains. So the external magnetic field tends to align the misoriented spins in the domain wall, leading to its displacement. And this process can occur simultaneously as the field increases. So what you have over here is, as you're increasing the H over here, you see how the magnetization is increasing. One is, in one particular level, what you will find is the domain wall itself is moving. And then at the higher level, what you will find is the domain wall itself is rotating. So rotation of spin is opposed by the increase in anisotropy energy, magnetocrystalline shape stress. So during rotation, all spins need not be parallel to one another, and the actual picture might get a little more complicated. So what is the effect of temperature? So that was how basically your magnetization is increasing. We say that with the magnetic field, application of magnetic field, how the magnetization is increasing. So with this different domains, whatever is there are two different ways. One is the domain wall motion, the other is the domain wall rotation. Then with the effect of temperature also, we see that spatially correlated collective quantized modes, they lead to demagnetization. So ferromagnets become paramagnet above Curie temperature. So at this Curie temperature, susceptibility becomes infinite. Even beyond Curie temperature, there are local clusters or spin clusters of these allied magnetic moments. So maximum magnetization is obtained when all the moments, they have parallel orientation. Okay. So it is expected that when you have a plot of this sigma s by sigma 0 versus T by Tc, they will approximately lie on one another for different materials. So if I now plot T by Tc, that is temperature by the Curie temperature on the x-axis, and if I have saturation magnetization, and along with it we have maximum magnetization when all the magnetic moments have parallel orientation. So if you are plotting this versus this, then what you will see is it is going to look like this particular plot. So it is going to go somewhat like this. So this is known as the demagnetization curve for a ferromagnet. This is the effect of temperature. So now let's see the domain structure and magnetization process. So as I said, the magnetic structure of a ferromagnetic material consists of domains. And why they consist of domains? Because they reduce the magnetostatic energy. So these domains are separated by domain walls. So broadly, there are two different kinds of domain walls. One is the block wall and the other is the Neal wall. So as shown is in this particular figure, the block walls, the spin vectors rotate out of plane in the domain wall, while in Neal walls, they rotate in plane. So Neal walls, they are seen in thin films. They are usually observed in thin films around 40 nanometer thick. Usually the domain wall thickness is few hundred atomic diameters, that is rather diffuse. Hence the domain wall by itself is a nanostructure. So what this actually means, so in case of a block wall, so this is a crude schematic as you can see over here, as the number of spin involved in the wall is much larger and hence rotation between adjacent spins, they are much smaller. So this is what you see in case of a block wall. Okay. The domain wall represents a region of very high energy. So as the spin vectors are not in direction of easy magnetization. Hence thicker walls represent higher energy, and in materials with higher magnetocrystalline anisotropic energy, the domain walls are generally thin. And other sources of anisotropy are those due to shape of the particle and due to residual stresses. A competition between magnetostatic energy and magnetocrystalline anisotropy energy essentially decides the domain size and shape. The word essentially has been used as other factors like magnetoelastic energy due to magnetostriction, which is change in dimension due to magnetic field, also contribute to the overall energy. So the total energy, it can be written in terms of four terms, sum of four terms. So one is exchange energy, the other is anisotropy energy, then there is magnetoelastic energy, and there is external energy. This external energy corresponds to the energy of total magnetic moment in the external magnetic field. So these are the different types of energies which are present in the particular material. So now we discuss what is magnetostriction. So a magnetostrictive material will change shape when it is placed in the magnetic field. Okay, so most ferromagnetic materials exhibit some measurable magnetostriction. Since the phenomena involves a bidirectional energy exchange between magnetic and elastic states, these materials provide a mechanism for both actuation and sensing applications. They are also successfully employed in a wide variety of devices for vibration control of mechanical equipment. So what you have, with the current flowing, the length of the rod increases by a small amount, delta L. So once the current is flowing through this particular wire, what you find is this length of the rod, it changes. So it was L before. Once you are passing current, it changes to L plus delta L. And this strain, this delta L by L is called magnetostriction, for which this symbol lambda is used. And magnetostriction is a second order effect. So you have to understand that when you are applying a particular field over here, you are applying a particular magnetic field. In that case, you will find this change in length happening, or the strain is observed, and this is known as magnetostriction. So the principal magnetostrictic effects which are observed experimentally are, one is the Joule effect. This can be an extension or contraction in the same direction as the magnetic field or in some other direction. Then you have a volume effect or volumetric expansion. This is a very weak effect. You can have the Weidmann effect. It's a shear strain response to the magnetic field, analogous to the tensile or compressive strain which is produced in the Joule effect. Or you can have Filari effect. There is a change in the magnetic permeability in response to applied stress. This is also referred to as a magnetostrictic effect or a magnetomechanical effect. So these are the different principal magnetostrictic effects which are observed experimentally. So why magnetostriction occurs? Why do we see this change in the length or change in strain or whatever it is? So you have to understand that when an external magnetic field is created, the domains which are aligned most closely with the external field will grow, while all the other domains will be reduced in size. So now, depending on the orientation of the crystal, there will be some cases where electron orbitals cannot become aligned to the direction of the external magnetic field without a change taking place in the distances between the atoms or ions, and these distances must increase to allow the orbitals to become aligned. So these changes in length may cause the crystal structure to become elongated in the same direction as the magnetic field, or to become elongated in one or more directions at right angles to this direction. So in this last case, there may be a contraction of the crystal in the same direction as that in the magnetic field. So that is basically what gives rise to that entire magnetostriction effect. Now there is another thing which is known as magnetoresistance. What is this? As the name suggests, the resistance of a conductor changes when placed in an external magnetic field, and this is known as magnetoresistance. The resistance is higher if the field is parallel to the current and lower if the field is perpendicular to the current. So in general, the resistance depends on the angles between the current and the magnetic field, and this effect is known as anisotropic magnetoresistance, or AMR, and the change is usually very small, around 5%, but it can be as large as 50% in some ferromagnetic uranium compounds. Magnetoresistance arises from a larger probability of SD scattering of electrons in a direction which is parallel to the magnetic field, and AMR effect is used in magnetic field sensing devices. So now let's look into magnetism and nanomaterials. That is another very interesting field. So when we look into magnetic nanostructures in bulk materials, so even in bulk magnetic materials, some structures can be nanoscale, like the domain walls, as I said, in the ferromagnet. They can be in the form of, nanomaterials. And some domains, especially those in the vicinity of surface or grain boundaries, they themselves can be nanosized. Or you can have some spin clusters above paramagnetic Curie temperature, which could also be nanosized. So now when we go from bulk to only nanostructure, the nano only, then the structure sensitive magnetic properties like coercivity, they change significantly. So some of the possibilities when we go from bulk to nano. So these are the first three, like these domain walls and those some domains like vicinity of surface or spin cluster. These are when it's a bulk material inside which you have nanostructure. But some cases we go directly from the bulk to the nanostructure. In this case, what are the different cases? Like ferromagnetic particles can become single domain. Then what you see is super paramagnetism in small ferromagnetic particles, that is particles which are ferromagnetic in bulk. Then you see a concept which is known as giant magnetoresistance effects in hybrids or layered structure. Or you can have antiferromagnetic particles in bulk which behave like ferromagnets when it goes from bulk to the nano form. So what is this dependence of magnetic moment on the dimensionality of the system? So there is an increase in the magnetic moment per atom as we decrease the dimensionality of the system. So this is indicative of the fundamental differences in magnetic behavior between nanostructures and bulk materials. And you have to understand this effect is all the more noteworthy as surface spins, they are not all ordered along the same direction as the spins in the interior of the material. Thus, we expect nanocrystals with more surface to have less mu b per atom, that is per atom, than the bulk materials, and this is purely based on the surface effect. So if you look into the magnetic moment of nickel and iron, you see when you are going from bulk to a zero dimensional, you see there is an increasing magnetic moment per atom. So you can have a maximum possible moment of almost 6 Bohr magneton per atom. And this implies that the zero dimensional nanocrystals, very little of the orbital magnetic moment is quenched. So you see all these magnetic moment manifesting when you go from bulk to the nano domain. So now another very important concept when you come to nano is superparamagnetism. So you have to understand as the size of the particle is reduced, the whole particle become a single domain below a critical size. So what happens is a particle which is smaller than the domain wall thickness cannot sustain a domain wall. So then the magnetostatic energy increases as r cube, that is r is the radius of the particle, whereas the domain wall energy is a function of r square. So there is a particular critical radius below which domain walls are not stable. Okay, so the general trend is that this RC, or this critical radius, is a function of sigma by ms square. Ms is saturation magnetization and sigma is the magnetic moment per unit mass. So this is how the critical radius depends on these particular factors. So now if you see that if you are having a larger particle and then you are moving into a smaller particle size, so from multi-domain when you are moving to single domain, then at one particular point of time, there is an increase. So the multi-domain, there is increasing coercivity with the decreasing size. So you can see the coercivity which is plotted along the y-axis. You can see this coercivity is increasing with the decreasing size. It reaches in the single domain particle, it reaches a peak coercivity. And then when you're moving down from that single domain particle, so this again the coercivity starts decreasing with the decreasing size. And at the single domain particle, you have almost a zero coercivity. So when you have a single domain particle dp, then this is having a zero coercivity. So this is how basically we talk about how the coercivity changes when you are moving from a multi-domain to a single domain particle. Okay. So, and the superparamagnetism is thermal disordering effects dominate over tendency for spin alignment. So this is known as the superparamagnetic effect. So if you are looking into magnetism in thin films or hybrids, 2D versus 3D behavior. So in case of nickel films on copper, when the thickness of the nickel film is greater than 7 monolayers, the system behaves as a 3D Heisenberg ferromagnet, and below 7 monolayers, it will behave as a 2D system. So in the 2D system, all the spins are in plane, while in 3D system, out of plane spin orientation is also observed. What is the Curie temperature of thin films? So if you have this particular, if you are plotting TC versus the thickness in monolayers, you will find that as you increase the number of monolayers, what happens is this actually it goes and it kind of this TC by bulk, that is the Curie temperature by the Curie temperature of bulk, it will reach this level of 1, that is tends towards the bulk behavior as you increase the number of monolayers. So this is basically magnetism in thin films and hybrids. So magnetism of hybrids means what? There is an exchange anisotropy. So due to exchange coupling of spins across an interface, because now you have a hybrid, so you have different kinds of materials. In the interface, there is going to be an exchange coupling of spins between a ferromagnetic phase and an antiferromagnetic phase. And that is a preferred directional anisotropy for the field, which leads to a shift in the hysteresis. So what happens in the hysteresis, you will find that the HC values on both sides, they are not same. So on one side it's going to be more, the other side is going to be less. And then you say that there is an exchange anisotropy which is present in case of those kind of hybrids. So steps involved in creating exchange anisotropy are as follows. So you have a single domain ferromagnetic particle in contact with an antiferromagnetic layer. So you apply a field above the Néel temperature of the antiferromagnetic phase to saturate the ferromagnetic phase. You cool the system below the Néel temperature of the antiferromagnetic phase to introduce a preferential alignment of spins across the interface in the antiferromagnetic phase. And the spins in the ferromagnetic phase will maintain their orientation even after the field is removed. So now you construct this MH loop. So if the field is removed, the spins in the ferromagnetic phase will flip to the field cooled direction due to the influence of the antiferromagnetic phase. And as the field direction is reversed, the spins across the interface in the antiferromagnetic phase oppose the reversal of spins in the ferromagnetic phase. In the ferromagnetic phase, and hence the exchange coupling, it will lead to a very large coercivity value. So all what I said in the previous slide is kind of explained over here. So this is what you see. With exchange anisotropy, the field which was over here, the actual curve which was somewhere like this, it has now moved, and you see this, the coercivity is not equally distributed along, and what you see is there is a the coercivity is kind of skewed in one direction of that applied field, and this is known as the exchange anisotropy, and this you will find at the interface. Okay. So then you will find this different, when you are actually checking out any magnetic material in the nano domain, you generally find a lot of research papers will give you the ZFC and the FC curves. So what is the ZFC curve? The sample is cooled from zero field from T1, where all the particles are superparamagnetic to T minimum, which is at a constant rate. Then you apply a small measuring field, and then the sample is heated from this T minimum up to the high temperature, and then the magnetization is measured. So this is the zero field cooled magnetization curve plots. Then you have a field cooled magnetization. As the name suggests, the sample is cooled under an external magnetic field from this T1, where all particles are superparamagnetic, to T minimum at a constant rate. And then the sample is heated from T minimum to a high temperature and magnetization measured. So this is a field cooled magnetization. Okay. So in the first case, there is no field applied. In this case, which is a field applied. And then if you plot it, what you will find is that the ZFC and the FC curve, this is how it is going to look. Your ZFC curve is going to look somewhat like this, whereas your FC curve is looking like this. And then there is a kind of a point over here where you see there is a differentiation happening, and this is known as the blocking temperature. Okay, so you have something which is known as the blocking temperature. So above this, T irreversible, this tau value, or you can say this temperature value, this time value is so short that thermal equilibrium is always attained before completing a single measurement, and this is known as the superparamagnetic state. So this is the normally how the plot looks like, the ZFC and the FC plot. This is how it looks. So now you have to understand that this is how my M versus H is looking. Yeah, I have my HC over here. I have my magnetic saturation over here. This is the remnant magnetization, whatever I find when I actually bring back the field to zero. So some magnetization is still left in the sample. So then this is hysteresis loop, what you see at 5K, which is at a lower temperature. Then at B, what you see is temperature dependence of saturation magnetization MS and remnant magnetization. So this is how it is going to look. So with temperature, this is how your saturation magnetization is going to look over here, as is shown in this particular plot. Then C is showing you the temperature dependence of coercivity. So as your temperature is increasing, the coercivity value is decreasing. And then the D plot is showing you the temperature dependence of field cooled and zero field cooled susceptibility at the blocking temperature, which is this TB over here. This is this particular temperature. Both this remnant magnetization and the HC, they vanish. Whereas at ZFC susceptibility, they show a kind of a cusp-like feature. So this is basically how your different plots are going to look when you are moving into nano dimensions. So what are the application of magnetic materials? So many things we learned about bulk materials, nanomaterials. So you have certain application of hard magnetic materials. So the need for enlarged energy densities at different operating temperatures is the main motive for the development of rare earth permanent magnets. Most importantly, this comprises less dysprosium containing Nd2Fe14 B-type magnets with much improved temperature stability for electromotor applications at around 450 Kelvin. So these are the different hard magnetic materials which I have listed out over here. Later on you can look into this slide and you can find out the different materials and what is the magnetization. So hard magnetic materials, they have wide range of applications. In automotive, you use it for motor drives for fans, wipers, injection pumps. Telecommunication, it is used in microphones, in loudspeakers. Data processing, it is used in printers and stepping motors. Consumer electronics, in home computers, clocks. Electronics and instrumentation, you use in energy meter discs, sensors, dampers. Industrial application is in lifting apparatus, robotics. Astro and aerospace, you find it in auto compass, couplings, instrumentation. And in biosurgical, you have NMR and the MRI body scanner also. But then there are certain materials, as I said, where the coercivity value is very less, and these are known as the soft magnetic materials. So they are very significant for the subject of power electrical applications such as generators, distribution transformers, and a broad assortment of motors, as well as in electronics, where a mass of inductive components is required. And you find, this is how these are the different kinds of soft magnetic materials, and their permeability values are given over here. So soft magnetic materials, they find in DC a direct current application. In this case, what you do is the material is magnetized to carry out an operation and demagnetized at the last part of the operation. For material selection, the main consideration is permeability. High permeability is required for good material, and used in the field of magnetic shielding, electromagnetic pole pieces to activate the solenoid switch. Permanent magnet uses this material to make a path for flux lines. Whereas when you talk about AC application, the material will always be in magnetized state throughout the time of operation, and it is done by being magnetized in one direction to another in a continuous cycle. And for material selection, the main consideration is basically the energy loss in the system. The energy loss occurs because the material is cycled around the hysteresis loop. A good material should have a very small energy loss, and this is used in power supply, transformer, DC-AC converter, electric motors for making a path for flux in permanent magnetic motors, etc. So these are the different applications of functional magnetic nanoparticles. You can have these magnetic nanoparticles which can be used, as quantum dots, as nanodrugs, as metals. Then you can find application as antibodies or DNAs, ligands or receptors, dyes. It can be used for specific binding of drugs, drug delivery, bacteria detection, multimodal imaging. So these are all, it can be used in MRIs. You can also, there are different applications of these different functional magnetic nanoparticles. Now, as I said, magnetoresistance, this is the dependence of electric resistance of a sample on the strength of external magnetic field. So magnetoresistance is given by this value delta H, and this is resistance in the presence of field minus resistance at zero field divided by resistance at zero field. So this term giant magnetoresistance, it indicates that the value for delta H for multilayer structures, they significantly exceed the anisotropic magnetoresistance, which has a typical value within few percent. So magnetoresistance was something a few percent, but giant magnetoresistance, GMR concept, this shows that for different multilayer structures, this delta H value is really very high. Okay, so this was discovered by Grunberg and Fert in 1988. So this is a large change in electrical resistance, which is induced by the application of a magnetic field to thin films composed of alternating ferromagnetic and non-magnetic layers. And this change in resistance is in general a reduction is related to the field induced alignment of the magnetizations of the magnetic layers. So in the previous experiments, the film was composed of layers of iron, which is ferromagnetic, and chromium, which is non-magnetic, with typical thicknesses of a few nanometer, and the current was applied in the plane of the film. Whereas the giant magnetoresistance effects, it can also be obtained with a current which is perpendicular to the layers. And the origin of this giant magnetoresistance is the dependence of the electrical conduction in ferromagnetic materials on the spin state of the carriers, which is the electrons. So now you look into this, the giant magnetoresistance effect is the change of electric conductivity in a system of metallic layers when an external magnetic field changes the magnetization of the ferromagnetic layers relative to one another. So the effect size is defined as something like this. So R parallel and R antiparallel resistivities for the parallel and antiparallel alignment respectively. Sometimes you can use it as the parallel, or as the case may be, you can also keep the denominator as the antiparallel configuration. So what is the charm of this system? This lies in the fact that it enables a sensing of external magnetic field strength in electrical circuits in between two electric states of resistance. And the spectrum of successful application of GMR technology is broad. It ranges from applications in air and space or automotive industry, non-destructive material testing or compass functionality in mobile phones, to biomedical techniques like biometric measurements of eyes and biosensors, for example, for the detection of viruses. So let's see how it looks like. So this is the change in the resistance which you see of the magnetic multilayer as a function of the applied magnetic field. So what you have over here is the magnetization configuration, which is indicated by the arrows over here. You see, one is the ferromagnetic layer. This is the non-magnetic layer, again a ferromagnetic layer. Here, the magnetic moments are aligned in the same direction. Then when you are applying the magnetic field, it is moving to the other direction. So now from this going to this, you have one portion where both of them, where one of them, it actually changes the direction. And so in this particular point of time, the magnetization is 0. At this point, the magnetization is negative, whereas at this point, the magnetization is positive. So this is the magnetization curve for the multi-layer with the application of the magnetic field. So what is the origin of this giant magnetoresistance? So first you have to understand the electrical conductivity in metals. It can be described in terms of two largely independent conducting channels corresponding to the upspin and the downspin electrons, so which are distinguished according to the projection of their spins along the quantization axis. So upspin and the downspin electrons do not mix over long distances, and therefore the electrical conduction occurs in parallel for two spin channels. Okay, so the band structure in a ferromagnet is exchange split. So the density of states is not the same for upspin and the downspin electrons at the Fermi energy. So scattering rates, you have to understand, they are proportional to the density of states. So the scattering rates and therefore resistivities are different for electrons of different spins. So this rho upspin is not equal to the rho downspin. So it is assumed that the scattering is strong for electrons with spin antiparallel to the magnetization direction and is weak for electrons with spin parallel to the magnetization direction. So this is supposed to reflect the asymmetry in the density of states at the Fermi level in accordance with Mott's second argument. So the parallel aligned magnetic layers, the upspin electrons pass through the structure almost without scattering because their spin is parallel to the magnetization of the layers. And on the contrary, the downspin electrons, they are scattered strongly within both ferromagnetic layers because their spin is anti-parallel to the magnetization of the layers. So in short, what are you saying? In short, the thing is that for the anti-parallel aligned multilayer, this anti-parallel aligned multilayer, both upspin and downspin electrons are scattered strongly within one of the ferromagnetic layers because within one of the layers the spin is anti-parallel to the magnetization direction. Please focus on this particular diagram. So in one of the layers the spin is anti-parallel to the magnetization direction. Therefore in this case the total resistivity of the multilayer is high. And exactly the opposite happens in case when both of them are parallel to each other. Okay. So there are different types of GMR. So in this particular case, you have these four different cases I have given over here, A, B, C, and D. In this, the magnetic multilayer, the ferromagnetic layers are separated by a non-magnetic spacer layer. And due to antiferromagnetic interlayer exchange coupling, they are aligned antiparallel at zero magnetic field. And this is indicated by, this dashed arrow, which you can see over here. At the saturation field, the magnetic moments are aligned parallel. So again, you have these solid lines, as you can see, the solid arrows. When you have a pseudo pin spin valve, the GMR structure combines, this is now hard and soft magnetic layers. So due to different coercivities, the switching of the ferromagnetic layers occur at different magnetic fields, providing a change in the relative orientation of the magnetization. So this is when you have alternate hard and soft layers. When you have a spin valve, what you do is the top of the ferromagnetic layer is pinned by the attached antiferromagnetic layer. So this antiferromagnetic layer is kind of pinned over here, and the bottom ferromagnetic layer is free to rotate by the applied magnetic field. Whereas if you have a granular material, then the magnetic precipitates, as you see, they are embedded in the non-magnetic metallic material. In the absence of the field, the magnetic moments of the granules, they are all randomly oriented as is shown over here. And when you apply the magnetic field, then gradually the magnetic field will align the moments in a particular direction. So this is how you have these different kinds of giant magnetoresisting elements. So what is the application? Why do we need to have this giant? What is the major application? So the largest technological application of GMR is in the data storage industry. Okay. So the GMR read head sensor is a hard disk, and this is built using a spin valve. If you remember, in the spin valve, you have you have a pinned layer. You have a pinned antiferromagnet layer. The spin valve resistance demonstrates a steep change in the small field range where H is equal to 0. As the magnetic bits on the hard drive pass under the read head, the magnetic alignment of the sensing layer in the spin valve changes, resulting in the resistance change. So as the read head it passes over the disk, what happens? The free layer shifts its magnetic orientation to match that of the bit. So sometimes the direction of the free layer's magnetic field is aligned with the field of the pin layer, which never changes, and sometimes it is opposite. So when they are aligned, most of the electrons will share the same up or down spin. As some of the electrons pass through the layers in the form of the current, there will be minimal scattering. So the low resistance means the current will be detected and the computer computes one bit. Okay. And when the free layer's magnetic orientation switches to opposite that of the pin layer, then there is a much different result. The electrons in the two layers will now have what? Opposing spins. So as the current passes through the magnetized layers, those electrons will scatter in one or other direction, resulting in a much weaker current, and you will find a 0 bit. So this is how the reading happens, 1 bit and 0 bit. So this is all about the giant magnetoresistance. Now coming to the other topic, which is ferroelectrics. Now we talked about ferromagnetism. Similarly, you have something which is known as ferroelectrics, and in ferromagnetism it was all about magnetic dipoles. In this case it is about electric dipoles. So ferroelectricity is a characteristic of certain materials that have a spontaneous electric polarization, and that can be reversed by the application of an external electric field. So now if you apply a small electric field, so which is not able to switch domain alignments, then the material will behave as a normal dielectric, where your polarization is directly proportional to the applied electric field. Now if you keep on increasing this E, we start to flip domains and there will be a rapid increase in the polarization. So when all the domains are switched, we reach saturation. So now what will happen if this particular electric field is removed? So again what you see is something which is known as a polarization hysteresis, And over here, the essential feature of a ferroelectric is not that there is a spontaneous polarization, but that the spontaneous polarization, it can be reversed by the application of an electric field. So if you reverse the direction of the electric field, then this spontaneous polarization, it can be reversed. So now there is a very, good relation between crystallography and ferroelectrics. So the crystal classification of a material, it has immediate implication for ferroelectric effects. You know, there are 32 crystal classes. All these crystal classes has been taught to you in the first couple of lectures, if I know it correctly. So all these, all these different kinds of 32 crystal classes are there. Now, few of them I have marked with black. So this, you have to understand that 11 of them, the ones which I have been, kind of given in black, these are basically the ones which have center of symmetry, centrosymmetric. And so these will not support ferroelectricity. So these particular crystal class, if you have in this material, you know that they are not ferroelectric. Then there is one more. So out of this 32, now 11 are gone. Out of the 11, now there are 21 left. Out of this 21, there is something, if you look into it, there is this O. So this O point group or 432, this also excludes ferroelectricity. So now the remaining 20 classes, they all exhibit something which is known as the piezoelectric effect. Okay. So you have something which is piezo, 32 point groups, out of which 11 are centrosymmetric, 21 are non-centrosymmetric. One of them is an exception, which is that O group. That is also, it doesn't give you any kinds of piezoelectricity. Now you have 20 piezoelectric group, out of which 10 are non-polar. You leave them out. Now, apart from out of this 20, the 10 which are polar, they are all pyroelectric. And out of this 10 polar, the ones which have reversible polarization, these are ferroelectric. And the others, there are something which is non-reversible polarization. So you have to understand that basically ferroelectric is basically a pyroelectric material and a piezoelectric material, but all piezoelectrics are not ferroelectric. So as you can see over here, this is the relation between piezo, pyro and ferroelectric point groups. So now coming to perovskite, perovskite is a naturally occurring mineral with the chemical formula of CaTiO3. This is a prototype for many AbO3 materials which are very important in ferroelectrics. So it consists of a non-polar cubic basic building block, as you can see over here. So below the Curie temperature, these crystals, they undergo symmetry lowering distortions. So there are three phase transitions in barium titanate in the order of decreasing temperature from 120 degree to 5 degree to minus 90 degree. So what you will find is that it undergoes different types of, there's a change in the crystal structure. So what happens, the crystal symmetry of the four polymorphs are cubic, tetragonal, orthorhombic and rhombohedral crystal structure. So all of these phases, they exhibit the ferroelectric effect apart from the cubic phase. So the moment there's a distortion, you find that it becomes ferroelectric. This barium titanate, calcium titanate, they all become ferroelectric. Now coming to semiconductor memory technologies. So RAM, these we know are random access memory, which has symmetric read and write access time. So non-volatile memories, they have traditionally always been read-only memory until the advent of the floating gate technology. Floating gate technology produced electrically erasable memories such as flash and EEPROM. So these products allow for in-system programming, but read and write access times, they are dissimilar. In fact, the write access time is several orders of magnitude greater than the read access time. Now this ferroelectric random access memory, the application of ferroelectric in the random access memory, it leads to the development of a truly non-volatile RAM. Why? Because it combines the advantage of both random access memory and non-volatile memory. So the write advantages over flash or EEPROM and non-volatility makes it quite suitable for storing data in the absence of power. So you have to understand why we spoke about the ferroelectrics, because they find a lot of application in semiconductor memory technologies, particularly in FRAM. So we said that floating gate basics. So what is a floating gate? So it is a typical flash memory cell uses a floating gate to store a bit by the presence or absence of charge. So if a floating gate is not charged, that is neutral, then the device operates like a normal MOSFET. So a positive charge in the control gate creates a channel in the P substrate that carries a current from the source to the drain. As you can see over here, it carries a current from the source to the drain. If, however, the floating gate is negatively charged, then this charge shields the channel region somewhat from the then this charge shields the channel region from the control gate and prevents the formation of a channel between the source and the drain. So the threshold voltage is the voltage which is applied to this control gate, as you can see over here, at which the transistor becomes conductive. So the presence or absence of a charge results in a more positive or a more negative threshold voltage. So in the flash memory language, programming, putting electrons into the floating gate means writing a 0. Erasing or removing the charge from the floating gate means resetting the flash memory contents to 1. Or in other words, a programmed cell, it stores a logic 0, and an erased cell, it stores a logic 1. So you have to remember the floating gate is completely surrounded by an isolation layer. So this enables the floating gate transistor to be used as a non-volatile memory, but it also imposes the need to find ways how you can charge or discharge it. So what are these ferroelectric ramps? We said the ferroelectrics are important. The application is in ferroelectric ramps. So this is built on this ferroelectric technology. So the FRAM chip contains a thin ferroelectric film of lead zirconate titanate, which is commonly referred to as PZT. So the atoms in the PZT, they change polarity in an electric field, thereby producing a power efficient binary switch. However, the most important aspect of PZT is that it is not affected by power disruption. So it makes this ferroelectric RAMs a reliable non-volatile memory. So you have to understand there is a up polarization and there is a down polarization. So when this central atom moves down, this is a down polarization. When it moves up, it is a up polarization. The cation in the center, it has two equal and stable low energy states, and these states determine the position of the cation. So you applying an electric field across the crystal causes the low energy state or position to be aligned in the direction of the field, and conversely the high energy state in the opposite position. So the applied field will therefore cause the cation to move from high energy state to the low energy state, and this transition produces energy in the form of charge, which is generally referred to as the switch charge. So therefore applying an alternating electric field across the crystal will cause the cation to move from the top of the crystal to the bottom and back again. And so this is how basically your ferroelectric RAM is going to function. So now, what is the operation? So basic storage element is a ferroelectric capacitor. The capacitor can be polarized up or down by applying an electric field. If the ferroelectric capacitor is not switched when an electric field is applied, no change in the polarization state, so it will behave like that of a linear capacitor. But if it is switched, then an additional charge is induced. Therefore, the capacitance must increase. The ferroelectric capacitor is combined with an access transistor, a bit line, and a plate line, as is shown over here. You have the plate line over here, the bit line over here, and it forms a memory cell. So a write operation is very similar to a read operation. The circuit applies an electric field in the desired direction across the ferroelectric capacitor. So this is how a FRAM it operates. Now we'll talk about some other effect which is known as the magnetoelectric effect. What is magnetoelectric effect? It is characterized by variation, as the name suggests, a variation of the electrical polarization in response to an external magnetic field or an induced magnetization by an external electric field. So what? You apply a magnetic field, you see a change in the electric field, or vice versa. You change the electric field and you see a change in the magnetic field. So this electrical polarization is given by this chi EE plus chi EMH, or the magnetization is given by this chi MH plus chi MEE, where chi E is electrical susceptibility tensor, chi M is magnetic susceptibility tensor, chi EM is nothing but mixed magnetoelectric susceptibility tensor. So what is this mixed magnetoelectric susceptibility tensor? This chi EM is delta P by delta H, which is electrical polarizability by magnetic polarizability, whereas ME is delta M by delta E, again the same thing, magnetization change divided by the change in the electric field. And this phi is nothing but the thermodynamic potential. So the following equation happens in the vicinity of the phase transition point. So this chi EM is equal to chi ME, or T minus T to the power of 1 by T minus T, which is in the square root of it. Okay, this is how it looks. So what is the idea of a magnetoelectric effect? The magnetoelectric effect is the phenomena of inducing magnetic or electric polarization by applying an external electric or magnetic field, as shown in the way. So when you are having inducing magnetic field, you see an external electric field. You are inducing a magnetic field by applying an external electric field, or you are applying an external magnetic field, and what you are seeing is an induced electric field. And these effects can be linear or non-linear. with respect to the external field. In general, this effect depends on temperature, and so this is how you actually mathematically express this particular effect. So if you look over here, you have this electric field, you have the magnetic field, and you have this particular strain which is applied, and then you have magnetization, you have polarization, and again the strain factor which is coming in. So when you are coupling this E and H, this is what you get over here. So this is the magnetoelectric effect when you're coupling E and H. Whereas you can have a direct magnetoelectric effect where you can have a converse magnetic electric effect also. So now coming to what is multiferroics. So multiferroics is defined as materials that exhibit more than one of the primary ferroic order parameters in the same phase. That is formation of switchable domains. So you have ferromagnetism, that is spontaneous magnetization. You have ferroelectricity, which is spontaneous polarization. Ferroelasticity, which is spontaneous strain. So if you have a combination of ferroelectric and ferroelastic, this is a multiferroic. So the effects which you see are piezoelectric and electrostrictive coupling. If you have ferromagnetic with ferroelastic in the material, then it is piezomagnetic and you find a magnetomechanical coupling. And if you have a ferromagnetic with a ferroelectric, then it is magnetostrictive and a piezoelectric coupling. So if you look into this particular figure, you can see there are materials which are magnetically polarizable and there are materials which are electrically polarizable, among which there is a certain element over here which is ferroelectric, and among these magnetically polarizable materials which you have a subset which is ferromagnetic. And your multiferroic is basically that subset which has basically ferromagnetism as well as ferroelectricity. So this is a multiferroic material. And also you can have this magnetoelectric effect, where magnetoelectric effect is loosely defined as materials which has magnetic polarizability as well as electrical polarizability. Okay, so this is how it works. So a ferroic material is basically a material which exhibits either ferroelectric or ferromagnetic or ferroelastic ordering, a feature typically demonstrated by the presence of a well-defined hysteresis loop when the material is switched electrically, magnetically, or mechanically. So multiferroics are materials which possess more than one type of primary ferroic order in a single phase. So these are either rare earth manganites or ferrites or transition metal perovskite oxides. So the examples are like terbium manganite, you can have TbMn2O5, you can have holmium manganates like HOMN2O5, you can have LuFeO4, bismuth ferrite, this is one of the most important or most common multiferroic elements, manganites, yttrium manganite. So some non-oxides are also multiferroic, such as barium nickel fluoride BaNiF4 and spinel chalcogenides like ZnCr2Se4. These are also multiferroic materials. So a material which have the coexistence of long-range ferroic orders and strong coupling between pertinent order parameters such as composites based on magnetic materials as well as piezoelectric materials. So you can have ferrites like barium titanate, manganites like lead zirconate titanate, ferromagnetic materials, and you have lead zinc niobate or lead niobate alloys along with lead magnesium niobate lead titanate. So these are all the composites. So you can have additional control to input and store data. So what are the applications? You find applications in sensors of these particular materials, multiferroics in sensors, in multi-state memories, in actuators, device applications, in biomagnetic fields. So bismuth ferrite, as I said, in single phase, it exhibits magnetoelectric coupling at room temperature. So this is one material which exhibits magnetoelectric coupling at room temperature, which is very important because most of the other multiferroic materials, they don't show magnetoelectric coupling at room temperature. You really have to work at very low temperatures, which doesn't make them practically viable. So now there are two different types of multiferroics. One is type 1 and the other is type 2. So what is type 1? In this, magnetic and electric phases, they coexist within the same compound, but they have different microscopic origins and they are broadly independent of each other. Whereas type 2 are single phase multiferroics and the materials in which the ferroic order is induced by magnetism, which in turn suggests a very strong magnetoelectric coupling. So you have to understand, so this magnetoelectric coupling is very strong in case of type 2 single phase multiferroics, but this is not that strong in case of type 1 single phase multiferroics, because in this case they have different microscopic origins and they are broadly independent of each other. So what are the domains and the domain wall in type 1 and type 2 multiferroics? So in type 1, it looks somewhat like this on the left hand side. As you can see, you will have something which is a perfectly ferromagnetic wall, then you will have something which is a perfectly ferroelectric wall, and then you will have some regions where you have a multiferroic wall. So in type 1 multiferroic material, magnetic and electric order they emerge independently. So the respective domain patterns do not have to coincide, and domain walls can be either magnetic, which is shown in this blue wall, or electric as shown in the red. If the domain patterns they are coinciding, then a multiferroic domain wall is formed, which is this orange wall which you see over here. So the formation of a multiferroic domain walls point to a coupling between magnetic and electric order, which however is not required by symmetry in case of this type 1 multiferroids. Now coming to the type 2 multiferroids, what is the change? The magnetic order induces the electric order. Thus, ferroelectricity emerges jointly with a magnetic phase transition. Because of the interdependence of this electric and magnetic order parameter, all ferroelectric domain walls are also magnetic domain walls, and therefore multiferroic. So you see over here all these domain walls, whatever you see, they are all multiferroic walls. So we have given you all this Fe and Fm, and all these are basically the terminologies which are used that has been explained over here. So what is composite multiferroics? Because you don't have really too many single phase multiferroics at room temperature, and also whatever you have, they have very weak magnetoelectric coupling. So single phase multiferroics, they are not really very interesting for applications. So what you can do is actually you can develop multiferroic composite materials. So these composites, these are compounds in which the electric, magnetic and piezo order states coexist within the material. But unlike the single phase multiferroics, which are homogeneous compounds and chemically isotropic, composite multiferroics are characterized by the fact that the order phases are physically separated from each other within the multiferroic composite material. So the resulting magnetoelectric coupling in this case can be 100 times larger than that of single phase multiferroics. However, this is only observed at microwave frequency and in a very limited range of operation conditions. So what is the condition to observe very strong magnetoelectric effect in composites? These two individual phases should be in equilibrium. Mismatching between grains should not be present. The magnitude of the magnetostriction coefficient of the piezomagnetic or the magnetostrictive phase and the magnitude of the piezoelectric coefficient of the piezoelectric phase, this must be high. The accumulated charge, it must not leak through the piezomagnetic or the magnetostrictive phases, and the strategy for poling of the composites, you must also determine that. So there are various applications of these ferroic materials, out of which most of it is given in this particular slide. You can go through it. But one of the very good examples is the AC/DC magnetic field sensors. So magnetic sensors are what? They are devices that can detect without physical contact the creation or variation in magnetic fields of the surrounding environment. And from these changes, they derive information on the properties of the magnetic field itself, as well as the indirect properties of other entities such as direction, presence, rotation, angle, speed, electric currents, temperature, so on. So what is the equation? This magnetoelectric voltage coupling coefficient is this alpha H to the power V. So what you have over here is the thickness of the ferroelectric layer in case of laminates, or the thickness of the sample. T is given by that single phase composite. H is the magnitude of the magnetic field under measurement, and V is the voltage response of this multiferroic sensor. So a linear response is critical requirement in order to operate as a sensor. Coupling measured at intermediate angles between 0 to 180 degrees show almost a linear variation, as you can see over here, this linear variation of the sensor's response. This indicates the possibility of utilizing multiferroic sensors for direction detection and compass application. Okay. And then the biggest application, the future application is in multiferroic random access memories and multi-state memories. So when magnetic order and electric polarization are simultaneously displayed, a multiferroic element could essentially combine the advantages of this ferroelectric RAMs and magnetoelectric RAMs to form a non-volatile random access memory with multiple memory states. So two binary states could be encoded by a ferroelectric polarization state, and by integrating the multiferroic within a magnetoresistive multilayer, two additional binary states could be encoded in the resistance state of the multilayer stack. So what you have over here is, you can have, see, these different memory states. You have state 1, 0, 0, where you have resistance and polarization of minus P. State 2, 0, 1, where you have the resistance R and polarization of plus P. Then you can have state 3 of 1 0, where this resistization is, in the other direction, it's higher, and what you have, the polarization is minus p. Whereas you can have a state 4 where 1, where in both cases this is also positive and this is also positive. Okay, so MF RAM would operate as an all electric read write 4-state memory RAM, offering therefore less power consumption, more memory density, and non-volatility simultaneously. These are the potential applications of multiferroic materials, where you can actually have all electric read write 4-state memory using these kind of materials, if they can be actually used at room temperature. Obviously we saw that the single phase materials, it is very difficult to find proper magnetoelectric coupling at room temperature, and the extent of coupling is also very less. But using these composite materials, a lot of research is going on, probably these kind of applications can come in. So with this, we will end our entire discourse on magnetic materials, and later on we will cover the heterogeneous catalysis part, which is the last part of this particular portion.